and there were 16 outcomes, and we did one problem. What was that problem?
What is the probability that at least one of them orders chicken?
So we wanted to find the probability that at least one of them orders chicken. So what we did is we went and counted the outcomes that had C in them. So 1, 2, 3, 4, 5, 6, 7. And in total we have 16 outcomes. So the probability is 7 out of 16. Now, there is an important rule. Important rule in the sense it is a very trivial rule. It's very straightforward, very easy, but quite important in practice. If A is any event, then A superscript C, AC is its complement, and the sum of the probability of an event and its complement would equal to 1. If I move probability of A complement to the other side, then I have probability of A equal to 1 minus the probability of A complement. So Bayon asked me last time in the class if disjoint events are the same as complementary events. No, but we can come up with something, we can deduce something if we have A and A complement. So is the complement of A and A disjoint? Yes, but I can't say that if two events are A and B are considered that, and if they are disjoint, I cannot say that they are complements. So if they are complements, they are definitely disjoint, but if they are disjoint, doesn't mean that they are complements of each other. Does that make sense? Yes? Okay. Now, what does A superscript C AC mean? Conditioning. Not A. Anything that A is not is the complement of A, and this rule is what we call the complementary rule. If I exclude zombies, vampires, Schrodinger's cat, then the probability of being alive is the complement of being dead. Do you agree? Yes? Can you think of two other events that are complements of each other? We went through a bunch of them yesterday where events cannot happen at the same time. Those two events are disjoint. By definition, complementary events cannot happen at the same time, so they are disjoint.
Being hot and cold.
Being hot and cold, you could be warm. What's a good example? Probability of being hot and cold at the same time, they are complements of each other. What else?
this case would be none of them ordered chicken.
What?
In the problem.
Oh, well, we'll get to that. Patience, my young Padawan learner. We'll get there in a bit. What else?
Can't be heads and tails.
Can't be heads and tails when you flip a coin.
Can't be tall and short.
You can't be tall and you can't be short. They are complements of each other. Probability that you're standing up is the complement of probability of sitting down, provided those are the only two events. Does that make sense? Yes? Okay. That said, going back to that probability over there, probability that at least one of them orders chicken. What is the complement of at least one of them ordering chicken?
No one.
None of them ordering chicken. So I could write that as probability yes? Going back to this table, none of them orders chicken in the sense they're ordering something else. If you count the sample space, do we see chicken there? No. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes? So the probability that none of them would order chicken would be 9 out of 16. And what is 1 minus 9 out of 16? Algebra. How do you combine a number and a fraction?
You would change 1 to 16 over 16 and then.
You change 1 to 16 over 16 to get the, has a name.
7.
Yes, we'll get there, but it has a name.
Common denominator.
Common denominator. So the common denominator is 16. 16 minus 9 is 7. It is the same answer, correct? So in some cases, using, this is what Bayon was talking about, at least one and none would be a complement of each other. In some cases, finding an at least one probability using the complementary rule is actually easier when compared to finding an at least one probability directly. When I do distributions, binomial especially, you will know what I'm talking about. Are we clear? Yes? Going to erase, can I erase the top part? What is the probability that one orders chicken or the other orders pork? Again, the order matters in the sense I'm treating two persons as person 1 and person 2, so if I switch, it matters to me. So what rule should we use? What conjunction do you see? What? 1?
Or.
Oh, So last time I mentioned anytime you see or, what do we do? The unit, right? So let's call person ordering check-in as event A or C, how about that? And ordering pork as P. And what we're trying to find is the probability of C union P. It's not the probability of cup, it's union. So use the rule and tell me what answer you get. So if we use the rule, this is the probability of chicken plus the probability of pork minus the probability of chicken and pork, right? So first thing that you want to ask would be, are these two events independent of each other? Oh, excuse me, are these two events mutually exclusive? Are they mutually exclusive? In the sense, if one occurs, the other cannot occur simultaneously. No. These two events are not mutually exclusive, so that probability cannot be zero. C and P occurring simultaneously once, twice. Yes? So minus 2 out of 16. Probability of C is the probability of ordering chicken. 1, 2, 3, 4, 5, 6, 7. Probability of B should be 7. 1, 2, 3, 4, 5, 6, 7. We have a common denominator. (14 minus 2), 12, 12 out of 16. If you simplify it, it is 3 over 4. 3 over 4 is 75%. Does that make sense? Yes? Okay. When we had union, multiplication rule is used when we have intersection. In other words, the conjunction that you see is and. A logical and, or the intersection. So naturally you may say, well, I could have used the multiplication rule in the previous problem. We cannot use it in the previous problem when we had C and P. And I'll tell you why. This can only be used when events are conducted in trials. By trials, I mean, occurrences, one at a time. If you go back to the concept of disjoint events, I kept using the term simultaneously, 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 in the sense I'm looking at the events together of some sort. But when it comes to multiplication rule, we actually look at events that happen in succession or one after the other, and that is what we call in trials. What does the rule state? Well, it's going to vary depending on two conditions. Independent events, dependent events. Here is the question, is independent the complement of dependent? Just the word themselves. Yes? Yes. These two are complements in a literal sense. So if we have two events, the probability of A and B is simply equal to the probability of A multiplied by the probability of B. Hence the name multiplication rule. If A and B are dependent events, I am going to state that there are two possibilities. If A and B are dependent events, what are the two possibilities?
If A is dependent on that, and if B is dependent.
So either A is dependent on B or B is dependent on A. Depending on how you see the problem, if A depends on B, B has to happen first, so probability of B multiplied by the probability of A vertical dash B. A vertical dash B simply means the probability of A given B. In the sense, what is the probability of A now that B had occurred already? It has a special name. It is a conditional probability in the sense whatever happens to A is dependent on B. So there is a condition. So it is the conditional probability of A given that B had already occurred. Does that make sense? The second case, we just have to switch the letters, that's all. What should happen first if B depends on A?
A.
A has to occur first. So probability of A multiplied by probability of B given A. How would you interpret the second part?
Additional probability B given A.
This would be the conditional probability Good. When we collect a sample, it is always important to realize if the observations are independent or dependent. Regular statistics, every single method that you learn here, and 21, 22, the underlying assumption is that the observations are independent of each other in the sense that the sample is a simple random sample. They have the same probability of choosing or being chosen. But there is another field of statistics called Bayesian statistics, which deals with dependent events. And that is 2 steps harder, 2 levels harder than regular statistics. But we will just stick with independent events. But what does it mean, literally, to be independent in a statistical sense? Let's imagine I have a box, or some box. And, well, what's your favorite candy?
Jolly Rancher.
Huh?
Jolly Rancher.
Strawberry?
Jolly Rancher.
Jolly Rancher? Okay. Not bad.
Skittles.
Love Skittles. And you know what? My cat loves it more than I do. The moment I open that bag, he's right there. So let's say you have a box. You have 13 Jolly Ranchers and 16 Skittles. And I love to eat candy, so I have 3 different trials. So this is what I mean by trials. So first time I close my eyes and I'm going to assume that the packaging is identical, right? Or else, there would be bias. If the packaging is identical, I stick my hand after shuffling this box, grab one, right? You would like to know, well, what is the probability that I would pick a bag of Skittles the very first time? Do you follow the question?
29. Nope. 16 out of 20.
16 out of 29.
16 out of 29.
That was me being surprised.
Now,
that I added it.
me being me and the sweet tooth that I am, so I finish the entire bag and I go for the box again, shuffle, stick my hand in, grab the next item, and I'd like to know the probability that I get Skittles again.
15 out of 28.
15 out of 28. Why?
Because you subtracted the one that you just ate.
Because I ate one. So, did my second trial depend on the previous trial?
Yes.
Yes. So this is a conditional probability. This is the probability S given S. Yes? Well, too many S's. I close my eyes and then finish that bag, close my eyes, shake the boards, stick my hand in, grab another bag, and I'd like to know the probability that it would be a Jolly Rancher.
13 of 27.
13 over 27. Does that depend on the previous 2 trials?
Yes, only because it affects the denominator.
But it still depends on the last
Yes.
2, right? It's JR. Probability of JR given first Skittles, second Skittles, and so forth. If you have 100 trials, we can keep on writing this stuff out, but we have other ways to deal with it. The next case, I have 13 Jolly Ranchers, 16 Skittles, and let's say I'm a diabetic, but I can't help myself, I need candy. So the only way I find satisfaction is to grab a bag, feel it 10 times, and then put it inside the box, shuffle it, grab a bag, feel it 10 times, put it inside, because I'm a diabetic. That makes sense. So, what is the probability that I grab a bag of Skittles?
16 of 29.
So I grabbed it, felt it, imagined it, I put it back in. And what is the probability that the second time I get Skittles?
16 of 29.
Still 16 out of 29. Would it depend on the previous trial?
No.
No. So the second time I feel it and then put it back inside the box, shuffle it, grab another one. What is the probability? Let's say that I pick Jolly Rancher.
13 of 29.
13 out of 29. Yes. So each time I picked a candy, in the first case, I did not replace. Yes? In other words, I picked a candy out, I didn't put it back in. In that case, I did replace, so I picked something up, put it back in. From a sampling sense, this is what we call with replacement. Naturally, that would be called without replacement. With replacement sampling implies independence. Without replacement sampling implies dependence of the events. Does that make sense? Good? Okay. Can I erase this slide? So, a store sells gaming consoles, TVs, computers. This is what happened during the last Black Friday. The store sold 18 gaming consoles, 24 televisions, 10 computers, and gaming consoles and televisions together, 9 people bought it. Television and computer together, 4 of them bought it. And console and computer together, 16. Yes.
Is that including the frequency of just them above?
No.
Okay, so it's
Separate.
completely separate.
Yeah, the total number here would indicate the type of sale. So this would mean they sold only a gaming console. A person bought only a television, only a computer. A person bought both console and television. A person bought both television and computer. A person bought both console and computer. Does that make sense? Okay. We want to find the probability that a customer either buys a television or a computer this Black Friday. So a customer walks in and we'd like to know what are the chances that this customer would walk in the store, buy either a television or a computer. So probability of T or C, T union C. And in terms of the rule, this would be probability of T plus the probability of C minus the probability of T and C. Are the events disjoint in the sense, is it true that if a customer bought a television, that the same customer will not buy a computer simultaneously?
No, because
They're not mutually exclusive because a customer could buy both, and it happened 4 times in the past. 4 out of those 81 sales that happened in the past was T and C occurring simultaneously, so minus 4 over 81. Probability of T is 24 over 81. And probability of C is 10 over 81. Which gives us 30 over 81. Good. We want to find the probability that 2 customers go to the store and they just buy televisions. The first one buys television, the second one buys television. We're selling 2 televisions, that's all. So in this case, it doesn't matter, I'm treating them separately. How would we find this probability?
it would be the probability of T and then the probability of T dependent on T. So it would be 24 over 81. Then it would be 23 over 80.
Okay, so you're so close there, Bailey. So Bailey's argument here is this would be probability of 24 over 81 multiplied by 23 over 80. Now, do we have any other answers before I give you the answer?
Wait, would it be 23 over 81 because it still counts as a total sale?
Okay. Still close. Getting closer.
Doesn't it just stay as 24?
Times 24 over 81.
Repeat again.
24 over 81 times 24 over 81.
That is correct. What did you say?
I was saying the same.
Okay. So, now Bailey's confusion here is she is looking at this total 81 and she is thinking, okay, there are 81 electronic devices at the store this year. That's not what we're saying, right? Previous sales indicate this is what happened in the past,
Okay.
right? So we have 2 different individuals. They are completely unrelated, right? First one, so this is person 1. First one gets the television. Second one buys the television. So what we're looking for is the probability that the first person buys a television and the second person buys a television, correct? So I did not say anything about how these 2 are related, correct?
Right.
So they are independent of each other. So the second person doesn't care about the first person and vice versa. So that event is independent of that event, so how do we find the probability?
You just multiply the two.
You simply multiply. what is the probability that a person would buy a television based on last year's information? The probability that a person would buy a television is 24 out of 81. And that probability is the same for every customer based on that information. Do you agree? Yes? So 24 over 81 multiplied by 24 over 81 0.09, maybe 0.8 something.
0.087.
7, like 877.
Yes.
So probabilities are good typically if you have 4 decimal places. So we have 36 customers who go to the store, and we want to know what is the probability at least one of them buying only the gaming console event. In other words, either 1 or 2 or 3 or 4 or all 30 keep on going. Do you really want to sit there and compute all of those probabilities?
No.
No. There has to be an easier way. So probability Do you agree with that relationship? Are they complements of each other? Yes? No?
Yes.
Are they? Yes. So, probability that at least one of them would buy only a gaming console, in other words, that, is the complement of saying none of them would be buying only a gaming console. So none of them would be buying only a gaming console would imply that the first person did not buy only a gaming console. The second did not buy only a gaming console, and so forth, right? That's what none of them means. Well, so what is the probability of not buying only a gaming console based on previous history? What is the probability of buying a gaming console?
18 out of 81.
18 over 81. If that is the case, what is the probability of not buying only a gaming console?
63.
63 over 81. I'll just call it P.
Can you look at this chart, please? Thank you.
This class is actually not bad. All 30 individuals. For all 30 individuals, what are the chances that they all don't buy only a gaming console?
Do you have to add 30 as an exponent because you would have to do 63
That
over
is
81?
correct. So this would simply mean that the first person didn't buy only a gaming console, and the second didn't buy only a gaming console, and the third, and the fourth, and the fifth, and all the way up to 30. And all of those events are independent of each other, right? So I can simply keep on multiplying P multiplied by P multiplied by P. How many times?
30.
30 times.
36. Oh, 36, I'm sorry.
Oh, sorry, 36 times. So we have 1 minus 63 over 81 raised to 36 with 0.6. So the probability here is 99.98%, which, I mean, we're saying what are the chances? At least one of them would fly. In the past, 18 of them would hit, so very good chance, fairly good chance. Now, why is this type of problem important? A very good case that we use, this is separate from that, I just want to finish with this problem. It's used in epidemiology. Let's take a simple case. Now keep in mind, this is just a probability. We're not saying it just couldn't happen to you, but the risk is a certain amount of chance. Let's see. Suppose the probability of contracting an infection due to a risky act, could be whatever, is about 0.067. If someone exposes themselves to 50 such acts, what is the probability of contracting the infection? Now, the person's exposing themselves to 50 such acts. Now, what would it mean to contract the infection?
One of those 50x.
Huh?
One of those 50x,
Exactly one or at least one of those?
at least one.
Right. In at least one of those 50 acts, the person got exposed, right? We're not saying, oh, you got it once, you're not going to get it again. At least one of those 50 acts, you ended up contracting the infection. So this would be the probability that at least how do we find this probability?
Would it be 0.067 to the exponent of 50 like we did on the last
So
one?
Bailey says it's 0.067 raised 50. Is she right?
I don't know.
1 minus probability of not getting infected.
So 1 minus the probability of not getting infected. You may say, well, it doesn't matter, we're all going to die anyways. So why I calculate this probability? Doesn't matter. That was morbid. 1 minus the probability of none of the 50 acts resulted in an infection, right? So they are complements. Is the probability of contracting the infection is 0.067. What is the probability of not contracting the infection?
0.933.
0.933. Okay. So probability of not contracting is the complement of contracting the infection, so 1 minus 0.067, 0.933. Yes. So there, it will simply be, if we use the same logic, 1 minus 0.933 raised
50 to 50.
and what do we get?
0.9688 rounded.
0.9688. Now, change that 50 to 5 and tell me what you get.
0.293.
0.293. So if you get exposed, if you expose yourself 5 times, there's about a 29% chance. If you expose yourself 50 times, there is a 96% chance. But change that 50 to a 500. What do you expect to happen? You're guaranteed to get that infection. Does that make sense? So keep in mind, even though these are probabilities, it is still a gamble. Just like going to Las Vegas. You know, if you're good at gambling, you like taking bets, making bets, simply calculate the probability and act accordingly. Do not listen to me when it comes to this. Okay, any questions? No? Good place to stop. If you have questions, talk to me. If not, have a good weekend and good rest of the week.